Picture this. The entire electrical grid, the biggest machine humanity has ever built, was designed entirely around physical momentum. Massive, heavy turbines spinning in circles. But right now, we're rapidly replacing those spinning traditional generators with digital, non-moving solar and wind systems. So have you ever stopped to wonder, what exactly happens to the power grid stability when the spinning finally stops?
Welcome to this explainer. Today we're unpacking the incredibly complex journey of electricity, the renewable energy transition, and the hidden math that keeps it all from collapsing. We're going to look at the grid in a completely new way, starting way out at the macro level of continent-spanning wires and zooming all the way down to the micro level of mathematical safety nets. Here is our roadmap for today. We'll cover the anatomy of the power grid, the renewable energy challenge, fixing those grid stability issues, what happens inside the substation, and finally, grounding and fault safety. Let's get right into it.
Section 1. Anatomy of the power grid, or as I like to think of it, the macro highway.
It really helps to think of the grid as an incredibly complex, high-speed highway system for electrons. The journey kicks off at power generation, but we can't just send that raw power directly to your house. We have to step it up using transformers for high-voltage transmission. We're talking 115 kilovolts up to a massive 765 kilovolts. Why? Because pushing electricity over long distances at a low voltage results in a tremendous amount of energy loss. Raising the voltage minimizes that loss. Then, as it gets closer to your neighborhood, substations step that voltage right back down for safe, local distribution. Funny enough, despite the name, the transmission network isn't actually a perfect grid. For economic reasons, it's really a web of redundant paths. This setup is brilliant because it lets operators route power from any plant to any load center, actively choosing the route based on real-time power costs and path efficiency. Moving on to Section 2, the renewable energy challenge. This is where the disruption happens.
Here is the absolute crux of the issue, the stark contrast between traditional synchronous generators and modern inverter-based renewables. Traditional systems were built around synchronous generators. Think of giant turbines spinning at a coal or hydro plant. They act like massive, heavy flywheels. They possess real, physical, mechanical inertia that naturally resists sudden changes in frequency. But inverter-based resources, things like solar panels and wind turbines, they connect to the grid digitally. They offer almost zero physical momentum, and they provide extremely limited short-circuit fault current. We are essentially trading heavy, mechanical stability for digital efficiency.
If you look at this correlation, it is wild. As renewable energy penetration goes up, the overall physical inertia of the power system drops. And when that happens, any little disturbance in the system causes severe spikes in the rate of change of frequency. Without that heavy spinning mass acting as a shock absorber, a simple fault can cause frequency deviations that trigger automated load shedding. In plain English, rolling blackouts, simply because the grid reacted way too fast to a tiny glitch. Section 3. Fixing grid stability issues. If we're losing our physical momentum, how do we fix it? Engineers actually have some incredibly clever mitigation techniques for this. To fix frequency instability caused by low inertia, they use virtual inertia control, basically programming inverters to artificially mimic the momentum of a spinning turbine. For voltage instability, we use StatComs and grid-forming inverters. And to fix weak grid strength caused by low short-circuit capacity, we literally install large spinning motors called synchronous condensers onto the grid. They don't generate any power. They just sit there and spin to provide that missing physical inertia and reactive power support. Let's focus on grid-forming inverters for a second because they're a total game changer. Older renewable setups used grid-following inverters, which basically just passively matched whatever frequency the grid told them to. But grid-forming inverters are proactive. They actively build the grid stability by establishing their own voltage and frequency references. They act as a digital safety net, perfectly emulating the behavior of a synchronous generator, but without a single moving part. All right, Section 4. Inside the substation, let's zoom all the way into the micro level. Inside these facilities, transformers step voltages down, and smart reclosers act as self-resetting breakers. But the real high-stakes math happens with capacitors, and this all comes down to the power triangle. You see, apparent power, represented by the letter S, equals real power, P, plus reactive power, Q. Imagine a right triangle. Real power is the base, reactive power is the height, and the apparent power the utility actually has to supply. The angle between them dictates your power factor, which is just the cosine of that angle, or P divided by S. Now, a bad power factor, say below 0.85, means a bunch of your apparent power is just reactive overhead. The utility works harder to push the same real power, and they will absolutely hit industrial customers with massive demand penalties for being below that 0.85 mark. So here's the fix. Engineers install huge capacitor banks in parallel with the load. Capacitors supply leading reactive power that literally cancels out the lagging reactive power from heavy motors. The exact formula for the correction capacity you need is QC equals P times the difference between the tangent of your current angle and the tangent of your target angle. Add exactly that many kVAR of capacitance, and you shrink that triangle's height, dropping your reactive draw without touching real power. It's a multi-million-dollar trigonometric fix. Utilities usually target correcting to a power factor of 0.95 to 0.98. You don't want to overcorrect to 1.0 because that can cause severe voltage rise issues. In fact, quick scenario for you. Say a plant's power factor drops from 0.95 down to 0.70 overnight, but the total load hasn't changed. What happened? Most likely, a capacitor bank tripped offline, like a blown fuse, and the plant lost its reactive power support. That is a real-world troubleshooting pattern that happens all the time.
Which brings us to our final section, grounding and fault safety, or what I call the invisible math. When a massive short circuit hits a substation, like a direct lightning strike or a severe fault, thousands of amps need somewhere to go instantly. Beneath the substation is a massive buried mesh of copper wire and deep ground rods, extending well past the fence line. Its entire job is to secure multiple paths for fault currents to safely enter the earth, neutralizing the danger before it electrocutes workers or destroys equipment. But this isn't just burying wire in the dirt. It requires some intense mathematical modeling governed by the IEEE 82000 standard. Because here's the thing, real faults aren't perfectly clean symmetrical waves. When a fault strikes, it often carries a sudden, massive, unidirectional spike called a DC offset. To make sure the grounding grid doesn't literally melt in those first few critical milliseconds, engineers meticulously calculate something called the decrement factor. This accounts for that deadly asymmetrical voltage spike, ensuring the grid can survive the absolute worst-case surge scenario. And there's an incredible nuance here. The math has to account for the fault current division factor. When a massive fault occurs, not all of that deadly current enters the earth through the local grid. A lot of it actually travels back along overhead static wires or feeder neutrals. By calculating the exact symmetrical grid current, meaning only the specific portion of the fault current that actually flows between the grid and the surrounding soil, engineers avoid massively over-designing the system. This saves millions of dollars in copper while maintaining strict life-saving safety standards. So, we've traveled from high-voltage transmission lines all the way down to the microscopic equations governing a copper mesh in the dirt. I want to leave you with this final thought. The grid is rapidly evolving. We are actively trading physical spinning steel for digital, low-inertia solar and wind. But as everything gets faster and more decentralized, those invisible, mathematically designed safety nets are quite literally the only thing keeping the system from spiraling out of control. The big question is, as our grid transforms, will our math always be able to outpace the speed of catastrophic faults? Thanks for joining me on this explainer, and keep questioning how the complex world around you actually works.